Here we're being given this equation, e to the x times y minus y squared equals e minus 4. And then they give us some values for x and y here. And what they're actually asking us to do is find the derivative, dy dx, at that specific x and y value. So let's pull out our equation. We get e, and I got to tell you, anytime you have e to a power, you kind of want to write that in parentheses. It helps really in a lot of ways to see when something, a function is inside another function, especially when you're trying to take a derivative of it. So what we have here is a classic implicit differentiation problem. You know you're doing implicit differentiation whenever you see x's and y's kind of commingling together in the problem. You never see that on a standard just straight up power rule, quotient rule style problem. But again, we're still just trying to find dy dx. We're trying to find our derivative. So to do this, what you would do is you would wrap this whole equation in a set of parentheses, and you would ddx this thing. When I'm doing implicit differentiation, I have a rule that I follow, a little mantra that I say, which is every time I take a derivative, I get extra stuff. And what that extra stuff is going to look like always is it's going to look like d, and then kind of envision there being this little box on top over dy. And what you'll do is you'll take the derivative like you normally do, and the extra stuff will be d, and then you're going to fill that box in with whatever the letter is you took the derivative of, okay? So keep in mind as we roll through this that chain rule, product rule, quotient rule, all these rules still work. So I come in and I'm going to take the derivative of this e function. Well, e is what I refer to as a special case derivative. It's one of those derivatives that you just have to have memorized. If you do, you're good to go. If you don't, you're probably not going to guess it. So if f of x equals e to the x, the derivative of e to the x is just e to the x. However, as soon as that becomes anything more than just a basic x inside there, negative x, 2x, whatever, as soon as it's more than just your basic x, it's a chain rule problem. And so as we look at what we have going on over here, we definitely have something more than just an x inside our e. And so that means we're going to need to follow the chain rule. So when I do the chain rule saying that I use, the recipe I use goes d in times d out. The derivative of whatever got plugged in instead of that basic x times the derivative of the outside, which will just follow this rule here. When we look at our inside on this problem, the in for us right now is going to be x times y. And so when I go to find that derivative, that d in, I look at that problem right now and I say, okay, well, how would I solve that problem? Well, again, product rule, chain rule, all these rules still apply. I have two things being multiplied. So that means I'm going to need to follow my product rule. So my product rule recipe that I use goes f g prime plus g f prime. I label one chunk the f, I label the other chunk the g, and then I go find my g prime and my f prime of those pieces. So I break that out into a bite-sized problem. F is equal to x, g is equal to y. So now when I come through, I take the derivative of f prime. The derivative of x is 1. I just took a derivative, so I'm going to get my extra stuff. I'm going to get this d, I took the derivative of an x this time, so dx over dx. Then I go find my g prime. The derivative of y, power rule, that would just be 1. I took the derivative of a y, so this time I get a dy dx. So now to create that d in that I'm looking for in this situation, I would follow my product rule recipe. So that recipe says first go grab f. So I go grab f. Then we're going to multiply that by g prime. So that would be 1 dy dx. You could just write that as dy dx. We don't really need the 1 times. Then we get plus, go grab the g piece, which is y, and multiply it by the f prime. When I come and look at f prime, anytime you get a dx over dx, anytime those pieces match up, it's really like having a 5 divided by 5. those always cancel out. That's really just a 1. So dx over dx will cancel out, and so really I'm left with just 1 in that situation. So there is my dn. So I come back remembering that that was just a part of this larger problem here. So I'm taking the derivative of this first piece. The derivative of the inside is now going to be this stuff here. So this is x dy dx plus, and again, I don't need 1 times y, so I can simplify that as I go, and I get y. Now I have to do the second part of my chain rule, which is the d out, the derivative of the outside. The derivative of the outside on an e just follows the rule. It stays the exact same. So this is e to the x times y. And when we're doing the chain rule, because we're multiplying these things together, we don't need the extra stuff on the d out. The d out never gets extra. It's like the only piece of the puzzle when you're doing implicit differentiation that never gets extra. Now we'll just keep moving our way down the road here. So then we get minus the derivative of y squared would be 2y, following our power rule. Bring the 2 down, subtract 1 from the power. Took the derivative of a y, so I get a dy dx equals, and then as I come over here, e is a number, it's a constant. So the derivative of a constant, no matter what method we're using, would be 0. And then the derivative of -4 would also be 0. So right now, that's our derivative. And what we're going to do from here is we're going to end up solving for dy dx. Well, if I have values for x and y, if they're not asking me to just get a generic equation, I go ahead and I plug those x and y values in now. It just kind of makes algebra a little bit easier when you don't have all these x's and y's and dy dx's all over the place. So plugging in for x, I would have -1/2. Then I would get dy dx, that's what I'm looking for, plus plugging in for y, I would get a -2. So instead of a plus, I should make that a -2 right there. And then I'm going to get e raised to the x, which again is -1/2, times y, which again is -2. And then minus the 2 that was a part of the problem, plug in my y, which is -2, and then dy dx, and all of that equals 0 still. And then you're just going to keep kind of coming through and cleaning this up as you go. So there's not much really to do for a moment here on this front. That's going to stay the same for a second. I'm now going to clean up this. -1/2 times -2, that's going to get me just e to the first, so e. And then -2 times -2 is going to get me a +4 dy dx, and all of that equals 0. Now I need to get rid of these parentheses at the back end here. So to do that, we're going to just distribute this e back into everybody. So we're going to get -1/2 e dy dx, multiplying e by that first chunk, minus 2e plus 4 dy dx equals 0. And then the game here is always to get everybody that has a dy dx. So when you've got multiple dy dx's, you want to get everybody that has a dy dx on one side of the equals, and anything that doesn't, you want to move to the other side. So the easiest way to do that on this problem is to go ahead and just multiply or add the 2e over. So I get -1/2 e dy dx plus 4 dy dx is all going to equal 2e. And then a lot of times what you can do here is kind of clear out that fraction, clear out that -1/2. We're going to go ahead and multiply this entire equation by a -2 to get that out of there. And so then distributing that in, that's going to give us a positive, the fractions would cancel. -2 times -1/2 would get us 1 dy dx. Multiplying that down here would get us -8 dy dx. And then that's going to leave us with a -4e at the tail end. And that's just an algebra trick that they like you to use a lot of times, as when you're dealing with these problems, you want to clear that fraction if you can. Then now that I've done that, this is why we get everybody to have a dy dx on one side, is now I can factor a dy dx out of everybody. So then that leaves me with e minus 8 equals negative 4e. And then we'll just kind of bring this up here as we finish out this algebra because we're running out of room. We got just a little bit more to go. You know, these problems are tedious. They're not difficult, but they're long. So now that I've pulled that dy dx out, now that these two things are being multiplied, I can go ahead and just divide that across right now. And I end up with dy dx equals negative 4e over e minus 8. And so that's our answer. And sometimes, again, they want you to, you got to be prepared to do a little bit of algebra manipulation on your own answers to see what works. If I look at option C here, it's really, really close to what I have, but I'm off by a negative. And that's because what they are having you do now really is pull kind of a negative to the front on that 4e. And if I pull a negative out of the bottom here, that's going to leave me with negative. And then this would, pulling a negative out of that positive would give me negative e. Pulling the negative out of there would give me plus 8. And then the negatives cancel out. And if we rewrite this, we now have 4e over 8 minus e, just rearranging those. And that would be our final answer on this one. So implicit differentiation, the main idea is every time I take a derivative, I get extra stuff. And remember, chain rule, product rule, quotient rule always still work together, so you can't forget those. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.